We are passengers on a colossal structure, a spiral made of hundreds of billions of suns, threaded with invisible matter, spinning through the dark. Milky Way is not just our home galaxy, it is a living system, ancient, dynamic, and constantly changing. Every star, every cloud, every particle is part of a delicate gravitational ballet. And what we know about it is astonishing. Our galaxy stretches across more than 100,000 light-years, its disk so wide that light itself would take a human lifetime just to cross a fraction of it. It's a barred spiral, a shape sculpted by gravity over billions of years, with a dense central bar and majestic spiral arms that twist outward like cosmic rivers. But it's not a solid object. Milky Way is a flow. Stars orbit at different speeds. Gas drifts through arms. Dark matter binds it all together in a halo so vast we can't see its edges. The entire structure spins at hundreds of kilometers per second. Yet we don't feel a thing. To us it's invisible motion. The galaxy is old, older than Earth, older than the Sun. It formed from ancient fragments more than 13 billion years ago, long before our world existed. In that time, it's grown by devouring smaller galaxies, reshaping itself again and again, and it's still growing. We're not sitting in the center of it all. We're out on one of its spiral arms, orbiting the galactic core like a leaf caught in a slow, silent current. One full orbit takes about 230 million years, a single galactic year. The last time our solar system was in this position, dinosaurs had just begun to rule the Earth. Every star you've ever seen belongs to this galaxy. Every night sky is just a keyhole view of something so immense it defies intuition. And beyond what we can see, there are layers of structure, invisible fields, hidden mass ancient scars of collision that shape the galaxy's destiny. 100 truths are waiting here, some bright and simple, others buried in the dark. To understand them, we have to journey through the Milky Way itself, not from the outside, but from where we already are, inside it. The Milky Way is not a cloud, not a disk, and not a flat plate drifting in space. It's a layered, twisted structure, a spiral with depth scars and hidden skeletons. At its heart lies a dense central bulge, a crowded sphere of ancient stars wrapped around a massive black hole. From this core, a bar of stars stretches outward like a cosmic spine, tens of thousands of light-years long, rotating slowly, pulling entire spiral arms in its wake. This bar is one of the defining traits of our galaxy. We live not in an ordinary spiral galaxy, but in a barred spiral, a more complex and dynamic shape. Beyond the bar, the spiral arms unfurl like rivers of light. Each arm isn't made of solid matter, but of stars, dust and gas flowing through gravitational waves. Patterns of density where matter bunches together as it moves. Stars are born in these arms, drift away, and new stars take their place. The arms are not fixed, they are living, shifting patterns. The disk of the Milky Way is thin but vast, around 100,000 light-years across, and only about 1,000 light-years thick. This is where most of the stars are, including our Sun, orbiting in a giant flattened whirlpool of matter. But the disk isn't perfectly flat. It bends and warps at the edges, a gentle twist shaped by past collisions with smaller galaxies. This warp makes the galaxy look like a soft wave frozen in space. We don't live in a clean geometric diagram. We live inside a distorted spiral, a cosmic sculpture built over billions of years. Above and below this disk floats a halo, a ghostly sphere of old stars and invisible dark matter. This halo doesn't shine like the disk, but it dominates the galaxy's mass, holding everything together in its gravitational grip. And out on one of the spiral arms, halfway between the galactic center and the cold edges of the disk, is a small yellow star, our Sun, our home. What looks like a single glowing streak across the night is actually a vast layered system. A central bar, spinning arms, swirling disk warping halo wrapping it all like a cocoon. We aren't orbiting a single star. We are moving inside an entire architecture of motion, a structure so enormous that even light would need 100 millennia to cross it. This is the shape of our home, and it's far stranger than the pictures we draw in textbooks. At the centre of our galaxy, there isn't a lighthouse. There's a shadow that rules by gravity. Between curtains of dust and gas radio and infrared telescopes reveal a crowded stage. Young hot stars whipping around an invisible point, old stars moving like sparks in a furnace. Filaments of gas curling and snapping as if tugged by an unseen hand. Nothing here drifts. Everything is held. Their hidden anchor is Sagittarius A, a supermassive black hole. Not a hole in the way a pit is a hole, but a place where space and time bend so deeply that every path curves inward. We don't see the black hole itself. We see its signature, stars tracing tight loops, light stretched and reddened near the edge. Occasional flares when a pocket of gas wanders too close and is ripped heated, made to glow before it vanishes. The neighbourhood around Escarret is extreme. Stellar orbits are measured not in calm circular sweeps, but in sharp ellipses that swing close then fling outward again. Each loop is a test of gravity in its purest form. Some stars complete these daring arcs in just a handful of years. A blink for the galaxy, long enough for us to watch them change their speed and direction in real time. From those motions, we read the mass of the invisible object at the centre, a few million times the Sun compressed into a region smaller than the orbits we track. Closer in space becomes treacherous. Gas clouds stretch into streamers. Magnetic fields twist like braided wire. Friction and shock waves turn cold gas into radiant plasma, feeding a thin, hot accretion flow that sometimes brightens suddenly. Brief heartbeats from the dart. The central bulge around all this is a city of stars, ancient populations mixed with bursts of youthful clusters, chemistry richer than the outer disk, motions crisscrossing like traffic at rush hour. The bar of the galaxy funnels material inward, whispering momentum away until gas has no choice but to sink. Here, gravity recycles matter. Clouds collapse into stars. Stars die and seed the region with heavier elements. New clouds form again. Creation and consumption share the same address. Dust hides much of this from ordinary eyes. That's why we learn to listen in longer wavelengths. Infrared light that slips through the haze, radio waves that map spirals of ionized gas, X-rays that flare when something is torn and heated near the brink. Piece by piece, these windows sketch a living diagram of the core. The black hole's spin likely drags space-time itself, tilting the orbits of gas and stars, nudging the inner flow into warped processing patterns. Time runs differently here, not as a metaphor but as a measurable effect of strong gravity. A clock carried on a tight orbit would tick more slowly than one far away. In the core, this isn't philosophy, it's scheduling, yet the centre is not only violent, it stabilises. By anchoring the galaxy's deep potential well, the core helps set the pace at which the bar turns, and the spiral pattern breathes. Too quiet a heart and the inner disk would drift. Too active and the bar could choke on its own inflow. Balance is the miracle. Enough gravity to hold the plan. Enough turbulence to keep the material cycling. So when you hear supermassive black hole, don't picture an isolated monster. Picture an engine room. Pipes of gas in and out. Valves that open as orbits precess. Pressure that rises and falls in luminous pulses. An invisible flywheel that keeps the galaxy's choreography in time. The Milky Way's centre is not our destination, but it is our reference point, the place that defines around for everything else. From here outward, every arm, every cloud, every star dances to a rhythm set by a darkness. We can weigh map and even watch flicker, but never truly see. From the core outward, the galaxy unfurls, not in straight lines, but in grand curling arms that sweep through space like frozen waves. They are the most recognizable feature of our galaxy, and also one of its most misunderstood. The spiral arms are not solid structures. They are patterns, density waves moving through the galactic disk. Imagine traffic on a highway. Cars flow, but the traffic jam itself holds its shape and drifts slowly forward. That is how these arms work. Stars, gas, and dust flow through them, but the arms themselves are the jam, the places where matter bunches up for a while. There are several primary arms in the Milky Way. 2 of them dominate the outer disk, and 2 smaller arms weave closer to the centre. Our own star, the Sun, is not sitting on a major arm. Instead, it lives in a small spur between them, a bright lane called the Orion Arm. This is like standing on a side street between 2 galactic highways. The spiral arms rotate more slowly than the stars themselves. Each star races ahead and then eventually drifts back into the arm again, a rhythm that repeats over hundreds of millions of years. This difference between stellar speed and pattern speed is what keeps the arms from winding up and disappearing. They are stable, flexible, and persistent. Inside these arms, new stars are born. As gas clouds enter a denser region, they are compressed. Gravity takes over and they collapse into brilliant young clusters. This is why spiral arms glow so brightly. They're full of hot, short-lived stars blazing with blue light. When these stars die, the next generation is already forming nearby. The arms are both cradle and graveyard, but these elegant shapes are not smooth. They are threaded with dust lanes, dark rivers of gas, and interstellar grains that cut across the light. These dusty regions block visible light but glow in infrared, revealing cold nurseries hidden behind their veils. The same dust that hides the heart of the galaxy also weaves through its arms like smoke in water, and the arms themselves are not perfectly flat. The outer disk of the Milky Way warps upward and downward like a slow, gentle wave. This warp is a scar, evidence of gravitational encounters with smaller galaxies that once brushed past and twisted the edges. From above, the Milky Way would look like a glowing pinwheel, with a bright bar in the centre, and spiral arms stretching out in soft arcs. From within, it's harder to grasp. We can only map it through the positions of stars, the movement of gas, and the faint signatures of hydrogen. These arms are the living rhythm of the galaxy. They shape the flow of gas, the birth of stars, and the journey of our own solar system through space. We're not stationary passengers. We are riding the spiral. The Milky Way is not built from stone or steel. It is built from stars, each one a sphere of plasma, forged by gravity and burning for millions or billions of years. Together they shape the galaxy's light, its weight, and its history. Astronomers estimate there are hangtram tingoi sao in our galaxy, perhaps niuhon motngin lanson goitung song tren kat. Most are small, faint red dwarfs, barely visible even with powerful telescopes. A smaller fraction are stars like our Sun, bright enough to dominate their surroundings, and a tiny rare few are massive giants, shining with the brilliance of thousands of suns, living fast and dying young. These stars are not evenly scattered. They form patterns, layers, and families. Most belong to the galactic disk, where they orbit in vast, nearly circular paths. Here younger stars are common, formed recently in the spiral arms. They burn hot and bright, often surrounded by gas and dust. Farther out and far above the plane of the disk lie the ancient populations. The stellar halo is home to some of the oldest stars in the galaxy, stars that formed more than a myoibatinum truo. Long before the Sun was born, they are poor in heavy elements, their light softer, colder, their orbits tilted in every direction like scattered seeds. Between these extremes are the star clusters, stellar families bound by gravity. Open clusters are loose gatherings of young stars, like fireflies caught in the same breeze. They drift apart over time. Globular clusters are different. They are dense, ancient, and resilient, spheres of hundreds of thousands of stars orbiting the galactic halo. They are fossils, living witnesses of the galaxy's earliest days. Some stars move at ordinary speeds, others do not. A few rare outcasts are hypervelocity stars, flung out of the galactic centre or torn free by gravitational encounters. They cross the galaxy at incredible speeds, on paths that may never return, and while each star is a single point of light to the naked eye, many are not alone. Binary and multiple star systems are common, with two or more suns orbiting a shared centre of mass. Some whirl tightly together, others drift far apart, locked by gravity in an elegant silent dance. Every star contributes to the Milky Way's gravitational fabric. They move, collide, evolve and die. Supernovae enrich the gas between them with new elements, feeding the next generation of stars. In this way, the galaxy is not static. It is self-renewing, and somewhere out on a minor spiral spur, around an ordinary yellow star, on a tiny rocky world, a species looks up and wonders how many suns there truly are. The Milky Way does not end where the stars fade. Beyond the glowing disk, past the spiral arms and clusters, lies a vast invisible structure. It has no light, no colour, no edges we can see, but it outweighs everything that shines. This is the dark matter halo. Dark matter is not made of stars, gas or dust. It does not emit, reflect or block light, but it has gravity, and gravity is enough. It holds the galaxy together, binding stars that should have flown away long ago. Without it, the Milky Way's spinning disk would unravel like a carousel with no axle. Astronomers first uncovered this invisible mass by studying the speed of stars. Near the galactic centre, stars move quickly. Farther out, they should slow down. Just as planets orbit more slowly the farther they are from their star, but the stars at the edge of the galaxy do not slow down. They race through space too fast for the visible mass to explain. Something unseen is anchoring them in place. That something is a halo of dark matter. Its mass is estimated to be around 10 times greater than all the stars, gas and dust combined. Its size stretches well beyond the visible disk, perhaps more than 300,000 light-years from the galactic centre. The halo envelops the Milky Way like a transparent cocoon. We cannot photograph it, but we can trace its pull. The rotation curve of the galaxy, a plot of stellar speeds versus distance, remains almost flat. Instead of dropping away, that flat line is dark matter's signature. An invisible hand gripping the stars, globular clusters orbit through this darkness, swinging in long, elegant arcs around the galactic centre. Streams of ancient stars curve and bend, their paths shaped not by what we see, but by what we don't. Dark matter is the skeleton of the galaxy. It sets the scale of the Milky Way, defines the strength of its gravity, and stabilizes its spinning disk. It even shapes the orbits of the satellite galaxies, tiny companions like the large Magellanic Cloud, guiding them along unseen rails. We still don't know what dark matter truly is. It might be made of exotic particles, or something even stranger, but its effects are undeniable. Every star, every orbit, every motion we see happens inside this invisible halo. The stars are the face of the Milky Way. Dark matter is its bones. The Milky Way was not born in peace. It was built in battle, shaped by collisions, mergers, and a slow gathering of cosmic debris. Its smooth spiral structure hides a violent past. More than 13 billion years ago, the first building blocks of our galaxy were small, chaotic dwarf galaxies. They were bright, unstable, and crowded with young stars. Gravity pulled them together over cosmic time. They collided, merged, and became something larger. A growing gravitational seed that would evolve into the Milky Way. The outer halo of the galaxy still carries the fingerprints of these ancient encounters. Across the sky, tidal streams stretch like ghostly ribbons, rivers of stars torn from galaxies that no longer exist. They are not random lines of light, they are fossils, recording the collisions that built the galaxy's skeleton. One of the most important events in this story is known as the Gaia-Sausage-Enceladus merger. Billions of years ago, a dwarf galaxy plunged into the Milky Way. Its stars and clusters were absorbed, leaving behind tilted, stretched orbits that still sweep through the halo today. This single merger reshaped the early disk, thickened it, and changed the structure of the galaxy forever. The Milky Way continues to grow in the same way. Right now it is absorbing the Sagittarius dwarf galaxy, a small fragile neighbour being slowly torn apart. Its stars stream across the sky like light from a shattered necklace, wrapping around the Milky Way as they fall inward. Each merger leaves behind more than stars. It leaves behind energy, angular momentum and structure. The central bar may owe some of its strength to ancient impacts. The warp in the outer disk may be a ripple frozen in place from long-vanished galaxies. We can still read this history by measuring how stars move. Modern surveys like the Gaia mission track the positions and velocities of billions of stars. From this data, astronomers can rewind the clock, reconstructing the hidden choreography that shaped our home. The Milky Way is not a quiet island. It is a survivor of countless collisions, each one leaving behind traces in its halo, its disk, its very shape. And the story is not over. Another collision far greater than any before is already on the horizon. Our star is not fixed in space. It is on a long orbit, drifting through the galaxy like a tiny boat carried by a vast cosmic current. Every second the sun moves, and with it every planet, moon and living thing on Earth. The sun is located about 27,000 light-years from the galactic center. It sits on a quiet stretch of the Orion Arm, a small spur between two of the Milky Way's major spiral arms. This position is more than just a location. It is a perfect balance. We are far enough from the violent galactic core to avoid its chaos, but close enough to remain part of the galaxy's vibrant star-forming disk. Our star completes a full orbit around the galactic center in about 230 million years. That is one galactic year. The last time the sun was in this position, dinosaurs were just beginning to dominate Earth. Human civilization in comparison is a flicker, a fraction of that orbit. The sun's orbital speed is astonishing. It travels at roughly 220 kilometers per second, fast enough to circle the galaxy while barely leaving a ripple in the stars around it. And yet we feel none of this speed. To us the sun seems still, but the sun's path is not a perfect circle. It gently oscillates up and down through the galactic plane, like a leaf riding the surface of a slow wave. Each rise and fall takes tens of millions of years. This vertical motion is part of the rhythm of the disk, a quiet heartbeat we cannot feel but can measure. Over cosmic time, the solar system does not stay in one galactic neighborhood. It slowly drifts through different regions, sometimes through quieter interarm zones, sometimes crossing spiral arms rich in gas and newborn stars. Some scientists suggest that these changing surroundings may influence conditions on Earth, subtly shaping its climate and environment over millions of years. The sun's journey is layered. It orbits the galactic center. That center orbits within the local group, and the local group itself is carried through the cosmic web. We are riding on multiple orbits at once, drifting through the universe inside a vast invisible flow. Everything we've ever known, every mountain, every breath, every heartbeat, has happened on a moving world, around a moving star, inside a moving galaxy. The sun's journey is not a story we watch. It is a story we live. We often picture galaxies as silent, frozen spirals drifting through space. But the Milky Way is anything but frozen. It moves, it breathes, it changes. Right now, as you hear these words, our galaxy is in motion. At its center, the bar of stars slowly rotates like the axle of a cosmic wheel. This rotation is not fast, but it exerts a quiet power. It shapes the entire spiral pattern, guiding the flow of gas inward toward the core, setting the rhythm for the arms to follow. The spiral arms themselves are restless. They are not rigid structures, but waves, rippling, bending and twisting over time. Gravitational tugs from satellite galaxies, the pull of dark matter, and the internal flow of gas all contribute to this dance. The shape of the Milky Way is constantly being rewritten. Star formation continues across the galaxy. Massive molecular clouds collapse, birthing new stars inside the spiral arms. In the galactic center, gas swirls inward toward the black hole, occasionally flaring with bursts of energy. Every few years, a star is born somewhere in the Milky Way, and another quietly fades away. The disk itself ripples like the surface of a slow ocean. This galactic warp is thought to be a remnant of past interactions, a scar written into the structure. It shifts gently over time, reminding us that the galaxy remembers its collisions. The halo is alive too. Ancient tidal streams drift through it, remnants of smaller galaxies long since devoured. Tiny satellites orbit in looping paths, their slow descent stirring the outer regions like pebbles dropped into water. Vast flows of hydrogen gas surround the galaxy, drifting inward over millions of years. This infill feeds the next generations of stars, a steady breath that keeps the Milky Way alive. Even the rotation of the disk is uneven. Different regions spin at different speeds, stretching and shearing the material like taffy. From Earth, none of this is visible. The night sky looks still calm, eternal. But in truth, the Milky Way is a living system. Every second the sun travels hundreds of kilometers, the bar turns a fraction of a degree, and unseen stars are born and die. The galaxy does not wait, it is always moving, even when we cannot see it. The Milky Way is massive, but it is not alone. Orbiting in the darkness around it is a swarm of smaller galaxies, faint companions bound by gravity. They are called satellite galaxies, and they are as much a part of the Milky Way as its arms and stars. There are more than 50 known satellite galaxies surrounding the Milky Way. Most of them are faint and fragile, ghostly collections of ancient stars drifting through the halo. But a few are bright and powerful enough to shape the galaxy itself. The two most famous are the Large Magellanic Cloud and the Small Magellanic Cloud. They are easily visible from the southern hemisphere, glowing like detached pieces of the Milky Way. Their gravity is strong enough to tug on the outer disk, sending gentle ripples through the spiral structure. Their orbits are long stretched ellipses carved over billions of years of gravitational interaction. Dozens of other companions are far smaller, tiny ultra-faint dwarf galaxies that barely hold together. Some contain just a few thousand stars. Others are wrapped in their own dark matter halos, lingering fossils from the earliest age of the universe. Many of these satellites are being ripped apart right now. As they orbit, the Milky Way's gravity peels stars from their edges, stretching them into delicate tidal streams. These glowing trails wrap around the galaxy like strands of silk, marking where a companion passed and where it is slowly being consumed. The fate of the Large Magellanic Cloud is already written. In a few billion years, it is expected to spiral inward and merge with the Milky Way, adding its star's gas and dark matter to the growing giant. This is how galaxies evolve, not just by forming stars, but by devouring their neighbours. The Milky Way is not a quiet monarch. Its companions pull back. Their collective gravity shapes the outer disk, nudges the halo, and stirs the flow of gas in the outskirts. This is not empty space. It is a community of galaxies, each locked in a shared gravitational dance. The Milky Way may be the dominant partner, but it is surrounded by a quiet swarm of companions, orbiting together through the cosmic night. At the heart of the Milky Way, beyond the spiral arms and glowing bar of stars, lies something truly extraordinary. It does not shine, it does not move like a star. It is silent, massive, and invisible, yet everything in the galaxy orbits around it. This is Sagittarius A, a supermassive black hole. It sits roughly 27,000 light-years from Earth in the direction of the constellation Sagittarius. From our planet, it's hidden behind thick clouds of dust and gas, completely invisible to optical telescopes. For decades, astronomers suspected that something immense lurked there, a gravitational engine powering the motions of the central stars. but suspicion became certainty through precise measurement. Near this invisible point, entire clusters of stars race around at thousands of kilometers per second. Their orbits are not random. They follow perfect curves tracing the shape of a deep unseen well. By tracking these stars over many years, scientists could weigh the object at the center. The result was astonishing. Its mass equals about 4 million times that of the Sun, all packed into a region no larger than our solar system. Nothing except a black hole can explain this. And so Sagittarius A star revealed itself not through light, but through its pull. Despite its monstrous size, the black hole is surprisingly quiet. It is not devouring everything around it in a blaze of energy like the raging cores of some distant galaxies. Instead, it sleeps, feeding slowly, pulling in gas and dust at a gentle pace. This is why the Milky Way's center does not blaze like a quasar. Our monster is calm for now, but this silence is deceptive. Occasionally a star or a cloud of gas wanders too close. When that happens, gravity tears it apart, heating the material to millions of degrees. For a brief moment, the quiet center ignites with X-rays and infrared light. Then the flare fades and the monster sinks back into the dark. The stars near the black hole are some of the most extreme in the galaxy. They move so fast and come so close to the event horizon that their orbits can only be explained by Einstein's theory of general relativity. Watching them is like watching gravity at its purest space itself bending under an invisible weight. Sagittarius A star may be hidden, but its presence shapes the entire inner galaxy. The black hole at the center of the Milky Way may be invisible, but its influence is written into the motions of everything around it. The stars closest to it move like dancers caught in a perfect orbit, their paths curved by an immense gravitational well. Astronomers have tracked these stars for decades. Among the most famous is a star named S2, which follows a long elliptical orbit around Sagittarius A star. It completes one full loop in about 16 years, reaching speeds of more than 5,000 kilometers per second at its closest approach. That is fast enough to circle Earth in less than 10 minutes. The fact that S2 and other nearby stars can orbit something so small and yet so massive is the clearest proof that a supermassive black hole is truly there. These orbits also confirm something deeper: Einstein's theory of general relativity. The stars do not follow simple Newtonian paths. Their orbits precess the point of closest approach slowly shifts, exactly as Einstein's equations predict when space itself is warped by gravity. This region of space is not just an astronomical curiosity, it is a natural laboratory for testing the most extreme laws of physics. Sagittarius A star may not be as violent as the cores of some other galaxies, but it still commands the inner Milky Way. Its gravity stabilizes the swirling bar of stars and the dense nuclear cluster around it. Every orbiting star, every whirling cloud of gas, every wisp of dust in the central few light years is shaped by this unseen anchor. But black holes are more than gravitational wells. They also influence their surroundings through powerful feedback. When gas falls inward, some of it is swallowed, but some is flung back out at tremendous speeds. This can heat or disperse gas around the core, regulating how quickly new stars can form there. Even a mostly quiet black hole can subtly shape the evolution of its host galaxy. Sagittarius A star also reveals itself through radio waves. Although it emits almost no visible light, telescopes that can see in radio and infrared wavelengths have mapped a faint flickering glow at its position. This glow comes from hot gas spiraling near the event horizon, accelerated to incredible speeds before disappearing forever. For the first time in history in the year 2022, astronomers captured a direct image of this region using the Event Horizon Telescope. The picture did not show the black hole itself. Nothing can escape from within its event horizon, but it revealed a glowing ring of light, a shadow carved into space-time. It was the face of the monster. For now, the supermassive black hole at the heart of the Milky Way is quiet. but it has not always been this way, and it will not remain quiet forever. Evidence suggests that Sagittarius A star was once more active. Astronomers have found vast bubbles of hot gas rising far above and below the galactic plane, structures stretching tens of thousands of light years into space. These Fermi bubbles, named after the telescope that discovered them, are thought to be relics of a powerful outburst millions of years ago. In that ancient moment, the black hole may have fed rapidly, unleashing jets and winds that blew across the galaxy like a storm. Even a sleeping giant can awaken. All it takes is a single massive cloud of gas, a stray star or a cluster drifting too close. When that happens, Sagittarius A star could flare again, lighting up the galactic center with X-rays and radio waves, a quiet monster briefly baring its fangs. Over cosmic time, the black hole will keep growing. As stars pass nearby, some will be torn apart, their material added to its invisible mass. The occasional merger with smaller black holes from disrupted star clusters will also feed its growth. It is patient, a predator that hunts on a timescale of millions of years, but its influence goes far beyond what it consumes. The black hole acts as a gravitational anchor, stabilizing the central bar, shaping the orbits of stars, and helping to maintain the structure of the inner galaxy. Even if it remains quiet for billions of years, its presence will still guide the Milky Way's evolution. The ultimate fate of Sagittarius A star is tied to the galaxy itself. When the Andromeda Galaxy approaches and the Great Merger begins, the two supermassive black holes will spiral toward each other. They will dance a long, slow dance, losing energy through gravitational waves until they finally collide and merge into a single, even more massive black hole. The center of the new galaxy will be ruled by this colossal remnant, but that future is billions of years away. For now, Sagittarius A star waits in silence, a dark weight at the core of everything. It doesn't need to roar to rule. Its gravity speaks for it. The stars above us, the spiral arms, the galactic disk, they all move to the pull of an invisible heart. And at that heart, a monster sleeps. The Milky Way is not just a flat spiral of stars, it is a layered structure. A luminous disk floating inside a vast invisible sphere. This relationship between the disk and the halo shapes everything the galaxy does. How it spins, how it grows, and how it survives. The disk is the part we can see. It's a thin, glowing plane made of hundreds of billions of stars swirling gas and dark lanes of interstellar dust. Most of the galaxy's visible mass lives here. The spiral arms, the sun, the star-forming regions, all of it lies within this rotating sheet of matter, spanning more than 100,000 light-years across. It's a delicate structure, so thin compared to its width that it resembles a cosmic vinyl record spinning in the dark. Surrounding it almost like a protective shell is the dark matter halo. Unlike the disk, the halo doesn't shine. It stretches far beyond the visible edges of the galaxy, perhaps more than 300,000 light-years from center to edge. This is where most of the galaxy's mass hides. Without the halo, the disk could not spin as fast as it does. The stars on the outskirts would drift away like sparks from a dying fire. The halo isn't just empty space filled with invisible mass. It contains ancient star clusters, faint dwarf galaxies, and long tidal streams, the fossil remains of past collisions. Every one of these is moving through the halo, pulled into graceful arcs by its gravity. The halo is a quiet ocean, and the disk is the luminous surface floating above it. The relationship between these two components is a dance of forces. The disk rotates rapidly, its stars and gas locked into a flattened plane by their motion. The halo, by contrast, is mostly static, a massive spherical structure that anchors the entire system. It doesn't rotate in the same way, but its gravity gives the disk the stability it needs to survive for billions of years. This connection explains why the Milky Way can spin without tearing itself apart. The halo holds everything together, while the disk gives the galaxy its visible shape. The two are inseparable. The disk and the halo are not just separate layers stacked on top of each other. They're connected through a constant exchange of matter and energy. Every second material flows between them, weaving the visible and the invisible into one living system. Gas from the halo slowly rains down onto the disk. It's cold, diffuse hydrogen that has drifted through space for billions of years. As gravity pulls it inward, the gas settles into the disk, feeding star formation like a slow but steady river. Without this inflow, the spiral arms would eventually run out of fuel and fade, leaving behind a galaxy of aging stars. At the same time, the disk sends matter back out into the halo. Massive stars live fast and die young. When they explode as supernovae, they eject vast amounts of gas and heavy elements into space. Some of that material escapes the disk's gravity and rises into the halo, carving giant bubbles of hot plasma that expand for thousands of light years. This creates a galactic fountain, a cycle of inflow and outflow that keeps the Milky Way chemically alive. This fountain is more than just a poetic image. It regulates the balance of gas in the galaxy. The inflow keeps star formation going, while the outflow prevents the disk from becoming unstable or choking on its own gas. It's a delicate feedback loop that has operated for billions of years. The halo also contains cosmic relics, streams of stars and debris from smaller galaxies that were torn apart long ago. As these streams fall inward, they bring not just stars but dark matter, slowly reshaping the structure of the halo itself. In this way, the halo evolves too, even if it appears silent. Meanwhile, the disk responds to every nudge from the halo. As matter flows in, the spiral arms grow brighter and denser. As it flows out, the disk ripples and shifts. The two structures are constantly adjusting to each other, locked in a slow-motion conversation that spans cosmic time. Astronomers can observe this dialogue through radio telescopes. They detect faint hydrogen signals stretching far above and below the disk, the whispers of gas moving between the galaxy's layers. Some of these flows are gentle streams, others are turbulent rivers stirred by supernova winds and gravitational tides. This quiet exchange is one of the reasons the Milky Way has remained active for so long. Galaxies that lose this balance grow old and cold. But the Milky Way still breathes. The relationship between the disk and the halo is not a temporary phase. It is the backbone of the Milky Way's evolution. For billions of years, this quiet exchange of matter and energy has dictated the pace at which the galaxy grows, shines, and changes. The halo acts as a gravitational skeleton. It defines the scale of the galaxy and provides the deep well of gravity that holds the disk together. Without the halo, the disk would not be stable. It would warp and tear apart under its own rotation. The invisible mass around the Milky Way is what gives it structure and strength. The disk in turn gives the galaxy its luminous identity. It's the part that forms stars, glows with starlight, and creates the spiral arms that define the Milky Way's shape. Every change in the disk, every burst of star formation, every ripple of turbulence, every wave of supernova explosions echoes outward into the halo. The galaxy is not a set of isolated parts. It is a single living system. This feedback loop also sets the lifetime of star formation. As long as the halo continues to feed cold gas to the disk, new stars can keep forming. But if the halo's reservoir runs dry, the galaxy will slowly grow quiet. The spiral arms will fade, the disk will cool, and the Milky Way will drift into a quieter, redder future. The halo also stores history. Every merger with a smaller galaxy leaves behind new streams, new pockets of dark matter, new structures folded into its depths. The disk may be vibrant and ever-changing, but the halo is the archive, the memory of every encounter and collision. Over cosmic time, this interplay has shaped not just the Milky Way structure, but its destiny. When the great merger with Andromeda Galaxy finally arrives, the halos of both galaxies will collide long before their disks touch. The invisible skeletons will merge first, laying the gravitational foundation for the creation of an entirely new galaxy. The disk and the halo may look like opposites, light and dark, thin and wide, visible and hidden, but they are bound together. Their relationship is what allows the Milky Way to live, grow and evolve over billions of years. Every star that shines in the night sky owes its existence to this silent partnership. The Milky Way is not drifting through space alone. It belongs to a cosmic neighborhood, a loose association of galaxies held together by gravity. This neighborhood is called the local group. It is our corner of the universe, a quiet cluster of galaxies orbiting and interacting in a shared gravitational field. The local group contains more than 80 galaxies, though most are faint dwarf galaxies that orbit the larger members. At its heart are three major players: Milky Way, Andromeda Galaxy and Triangulum Galaxy. These three galaxies dominate the group's mass, while dozens of smaller companions swirl around them like fireflies around bonfires. The entire local group spans more than 10 million light-years from end to end. Within this space, gravity gently binds its members together, though the distances between galaxies are vast and silent. Each galaxy moves on its own path, but they all share a common future. The Milky Way and Andromeda are by far the largest. They sit only about 2.5 million light-years apart, close enough on cosmic scales to feel each other's pull. Their mutual gravity is slowly drawing them together, setting the stage for a colossal merger in the far future. The local group is not a dense cluster. Unlike the crowded blazing cores of rich galaxy clusters, our neighborhood is relatively quiet. Most of its galaxies are small, isolated dwarfs with weak gravitational pulls. Some orbit the Milky Way, some orbit Andromeda, and some drift alone in the dark like wanderers on the edge of a great plain. Despite its calm appearance, the local group is full of motion. Every galaxy is moving, orbiting, drifting, being drawn by invisible threads of gravity. The Milky Way itself is on a slow, inexorable path toward Andromeda, and everything within the group will eventually be swept into this future collision. For astronomers, the local group is more than just home. It is a laboratory. Because these galaxies are close, we can study them in detail. Their stars, their gas, their structure, their histories. They reveal how galaxies live and evolve not in isolation, but as part of a larger connected system. The Milky Way may feel immense, but it is only one voice in the quiet chorus of the local group. The galaxies of the local group are bound together by a shared gravitational field. Even across millions of light-years, their invisible pulls connect them like threads in a vast silent web. The Milky Way and Andromeda Galaxy dominate this web, together containing more than 90% of the group's total mass. The pull between these two giants is not weak. They are moving toward each other at a speed of about 110 kilometers per second. Though that may sound fast in cosmic terms, it is a slow, inevitable drift, a motion that will bring them together in roughly 4 billion years. This isn't a collision in the explosive sense we imagine with solid objects. Galaxies are mostly empty space. When they meet, stars will pass by stars, and the structures will merge in a slow gravitational ballet. Orbiting these two giants are dozens of dwarf galaxies, each one a faint island of ancient stars. Many of them are satellites of the Milky Way. Others belong to Andromeda. A few drift in between, following elongated orbits that span millions of light-years. Their movements trace out the gravitational shape of the local group, like sparks outlining an invisible fire. Triangulum Galaxy, the third largest member, is much smaller but still plays a role. It orbits Andromeda and may eventually join the Grand Merger as well, adding its stars to the future combined system. Even the tiniest dwarf galaxies, though fragile, contribute to this web of mass and motion. The local group is also moving through space as a whole. It is being drawn toward a distant region called the Great Attractor, a gravitational anomaly far beyond our neighborhood. The entire group, Milky Way, Andromeda, and all their companions, is drifting through the cosmic web at hundreds of kilometers per second, a fleet of galaxies sailing together through deep space. Although the local group is small compared to massive galaxy clusters, it has a well-defined gravitational boundary. Beyond this point, other galaxies are no longer gravitationally bound to it, and instead follow the expansion of the universe. Inside this boundary, everything shares the same fate. The Milky Way's place in this system is not static. Its orbit, its satellites, and its future are all shaped by the gravitational landscape of the local group. We are part of something larger, a community of galaxies tied together by gravity and time. The local group is just one small cluster in a vast cosmic landscape. It floats like a single island in an ocean of galaxies, connected to others by thin filaments of dark matter and rivers of gas. To understand the Milky Way's future, we must see not only its neighbours, but also the larger structure it belongs to. The local group is part of a massive region called the Laniakea supercluster, a gravitational basin containing tens of thousands of galaxies. Within this structure, entire galaxy groups flow together like streams feeding a cosmic river, and the local group is one of those streams drifting toward a distant gravitational centre. This larger structure is mapped not by light, but by the motion of galaxies. Astronomers track how groups like ours move through space, revealing patterns shaped by dark matter on colossal scales. The local group is not fixed. It is slowly falling toward the Great Attractor, a mysterious region of enhanced gravity hundreds of millions of light-years away. Compared to the enormous clusters at the heart of the supercluster, the local group is quiet and modest. We do not live in a dense, turbulent galaxy cluster, where collisions happen constantly and galaxies burn bright with rapid star formation. We live in the cosmic suburbs, a calm, stable neighbourhood on the edge of something far larger. This quiet position has shaped the Milky Way's entire history. Because it is not trapped in a violent cluster core, it has been able to maintain its disk structure for billions of years, forming stars at a steady pace rather than burning out in a single blaze. Our galaxy owes its spiral arms, its stability, and even the existence of its habitable zones to this peaceful location in the cosmic web. But even in this quiet corner, the local group is not immune to destiny. Over billions of years, it will likely merge with other nearby groups, forming a larger structure, perhaps a small cluster of its own. Eventually, these structures may drift together under the pull of dark matter, their shapes stretched and folded into something new. From a human perspective, this is unimaginable time, but for the universe, it is simply the next step. The local group is not permanent. It is a chapter in a much larger story. The story of cosmic structure growing, collapsing, and merging over eons. The Milky Way, Andromeda, and all their companions are part of this vast choreography. We are not just residents of a galaxy, but participants in the slow, majestic dance of the cosmic web. In the stillness of the night sky, Andromeda Galaxy looks calm, a faint misty patch of light barely visible to the naked eye. But behind that calm appearance is motion. It is not drifting away like most galaxies in the expanding universe. It is moving toward us. The distance between Andromeda and Milky Way is about 2.5 million light-years. That seems impossibly far, but their mutual gravity is strong enough to overcome the expansion of space between them. Andromeda is on a collision course closing in at roughly 110 kilometers per second. This is not a guess. Astronomers have measured it with precision. Using space telescopes, scientists tracked tiny shifts in Andromeda's light. The Doppler effect, the same principle that makes a passing siren change pitch. That shift reveals not only how fast Andromeda is approaching, but also the direction of its motion through space. Over years of careful measurement, the evidence became undeniable. The two great spirals are moving straight toward each other. Unlike many galaxy encounters, this one will not be a glancing touch. It will be a head-on collision, a slow but unstoppable embrace shaped by gravity itself. The estimated time of impact, about 4 billion years from now, on cosmic timescales that is soon. But calling it a collision is misleading. Galaxies are made mostly of empty space. When they meet, their stars will not crash into each other like cars on a highway. Instead, they will pass through almost entirely unscathed. The real drama will happen on the grand scale. The shapes of both galaxies will stretch, twist and tear, their stars flung into new orbits like dancers in a slow-motion storm, the supermassive black holes at their centres, Sagittarius a star in the Milky Way, and Andromeda's central black hole will also begin their own long spiral, a dance that will end in one of the most powerful mergers in cosmic history. We live in the quiet before a storm we will never witness. The collision will not be sudden, it will unfold over billions of years, a slow-motion transformation on a scale almost too vast to imagine. The first encounter will happen when the outer halos of the two galaxies touch. This will occur long before the visible disks collide. The halos, vast spheres of dark matter stretching hundreds of thousands of light years, will begin to overlap, locking the galaxies into a single gravitational system. From that moment on, their fates will be bound. As the galaxies draw closer, tidal forces will twist their shapes. The elegant spiral arms of both galaxies will stretch like taffy, creating long tidal tails that arc into intergalactic space. Stars will be pulled from their original orbits and launched on wild trajectories, some flung far into the outskirts, others sent plunging toward the centres. Eventually the disks will pass through each other. To an observer watching from a distant galaxy, it will look like a grand ballet, two luminous whirlpools merging in slow spirals. Despite the chaos, almost no stars will collide directly. The distance between stars is simply too vast, but their orbits will be rearranged. The familiar spiral shape of the Milky Way will be gone, replaced by distorted streams and glowing arcs of scattered stars. During this time, massive bursts of star formation may ignite. Gas clouds that were once drifting peacefully will slam into each other, triggering waves of stellar birth across both galaxies. The night skies of any inhabited worlds would be filled with breathtaking vistas, sheets of light, vast streams of stars, and brilliant new clusters blazing into life. After the first pass, the galaxies will drift apart slightly, still tethered by gravity, but they will not escape each other. Their mutual pull will reel them back in. They will fall together again, each pass drawing them closer, each encounter shredding their structure further. Through these cycles, the Milky Way and Andromeda will stop being two galaxies. They will become one, a swirling chaotic structure in the process of rebirth. At the heart of this slow collision, their central black holes will begin their own gravitational dance, spiraling closer with each orbit, shaping the future core of the new galaxy. This is not the end of the Milky Way. It is its transformation. After billions of years of slow gravitational choreography, the two galaxies will finally settle into a single structure. The spirals that once defined the Milky Way and Andromeda will be gone, their elegant arms erased by tides and time. What remains will be a new galaxy, larger, rounder and brighter than either of its parents. Astronomers already have a name for this future system, Milkomeda. It will likely resemble a giant elliptical galaxy, a smooth glowing sphere of stars with little trace of its spiral origins. The new galaxy will contain nearly 1 trillion stars, drawn from both systems and from the tidal streams cast into intergalactic space. The central region will be dominated by a single supermassive black hole, the product of the merger between Sagittarius A and Andromeda's black hole. Over millions of years, the two black holes will spiral toward each other, radiating gravitational waves into the cosmos. Their final collision will release an enormous burst of energy, a ripple through space-time that will travel across the universe. This merged black hole will anchor the new galaxy. Its gravity will shape the stellar distribution, stabilizing the heart of Milkomeda just as Sagittarius A star once anchored the Milky Way. For any surviving stars, their orbits will be entirely different. Many will have been thrown into elongated paths far from the center. Others will settle into new stable orbits in the remnant core. The familiar constellations we know today will be erased long before the merger is complete. A night sky seen from Earth, if Earth still exists, would be unrecognizable. Star formation in Milkomeda will eventually slow down. Much of the gas will have been consumed or blown away during the collision. Over time, the galaxy will age and redden, its young hot stars fading as new ones are born less frequently. It will enter a quieter phase of cosmic life, a grand glowing giant drifting through the dark. But this is not destruction. It is transformation on a scale beyond anything we can imagine. The Milky Way's story will not end in fire. It will live on in a new form. Its stars, its black hole, its legacy woven into a new cosmic structure. Billions of years from now, the local group will be reduced to a single massive galaxy. And in the deep silence of space, Milkomeda will continue to shine. For billions of years, the Milky Way has drifted through the universe like a vast luminous river. It has no single beginning that we can witness, and no fixed shape that will last forever. It is alive not in the way a creature lives, but in the way a system breathes. Its stars are born in the cool darkness of spiral arms, live brilliant lives and die in explosions that feed the next generation. Its spiral pattern slowly rotates. Its bar turns through the core. Its halo holds everything in place. Every motion, every orbit, every glowing star is part of a larger rhythm. The Milky Way is not a frozen image in space. It is a process. The disk grows and shifts. The halo absorbs ancient streams, and the galaxy evolves. Its spiral arms are not static lines of stars. They are waves of density flowing through the disk like music through air. What we see in the night sky is a single frame in a film billions of years long, and we are part of it. Our star is just one among hundreds of billions, riding quietly through the Orion Arm. The entire history of humanity, every story, every dream, has unfolded during a tiny fraction of one orbit around the galactic center. We are travelers aboard a moving world, on a journey we can neither steer nor stop. Yet despite its constant motion, the Milky Way has given us stability. Its calm position in local group, its balanced structure, and its steady pace of star formation have made it a cosmic cradle. For billions of years it has quietly turned, building the conditions that made life possible. But nothing in the universe is permanent. Galaxies collide, merge, evolve. The Milky Way itself is heading toward a grand transformation. Its spiral arms will fade, its stars will be scattered into new orbits, its core will be reborn in a new form. It will not vanish, it will change. The Milky Way has existed for more than 13 billion years. Before our star was born, before Earth formed, before life even existed, the galaxy was already spinning in the dark. Countless generations of stars have lived and died here, each one adding its light, its elements, its story to the whole. We arrived late. Our solar system joined the galactic dance less than 5 billion years ago, a newcomer in a story already ancient. And yet in this brief moment, we have gained the ability to look outward and glimpse the structure that cradles us. When we look up at the night sky, we do not just see stars, we see the disk we are inside of. The faint band of light arching overhead is the cross-section of our galaxy. Billions of suns woven together into a single glowing river. We are looking along the spiral arms, through dust and starlight, across unimaginable distances, but this view is temporary. The Milky Way we know is not eternal. Its arms will one day be torn and reshaped. Its stars will scatter into a new configuration. Its name itself may fade, but its essence, the matter, the energy, the gravity that built it will endure in a new form. This is the nature of galaxies. They do not end, they transform, And yet the fact that we exist here, in this tiny window of time, able to understand even a fraction of this vast story, is extraordinary. We are not the centre of the galaxy, we are not its purpose, but we are its witnesses. Our world moves with it, our star orbits its heart. We live inside something far larger than ourselves, a living galaxy in a living universe. And when we look up into the night sky, we are not just seeing stars, we are seeing home. In the beginning, the Milky Way did not yet exist. The universe was still young, only a few 100 million years after the Big Bang. The first structures were forming out of dark matter invisible clumps that gathered like scaffolding in the cosmic night. Into these dark halos, hydrogen and helium gas fell cooling and condensing into the first stars. Our galaxy was born not from a single explosion, but from the slow assembly of many small pieces. Ancient dwarf galaxies, bright and chaotic, merged together under gravity's pull. Each collision was like a spark in the darkness, building something larger and more complex. Over hundreds of millions of years, these fragments joined to form the early core of what would become the Milky Way. The first stars in these early systems were massive and short-lived. They burned through their fuel quickly, then exploded as supernovae, enriching their surroundings with heavier elements. These explosions seeded the young galaxy with the materials needed for future generations of stars. Around the forming core, a halo of old stars and dark matter grew a silent skeleton that would hold everything together. One of the most important moments in this early history was a massive collision known as the Gaia, Sausage and Enceladus merger. A dwarf galaxy plunged into the young Milky Way, its stars torn apart and absorbed into the growing disk and halo. This event reshaped the structure of the galaxy, thickening its disk and leaving behind streams of stars that still orbit today. These tidal streams are fossils, quiet evidence of violent beginnings. As more material fell in, the galaxy flattened into a rotating disk. The first spiral patterns began to emerge, faint and unstable, guided by gravity and the movement of gas. Star clusters formed in bursts. Supernova winds blew gas outward while gravity pulled it back in. Slowly, the galaxy found a balance between creation and collapse. The oldest globular clusters still orbiting the Milky Way today formed during this chaotic time. They're among the most ancient objects in the galaxy, witnesses to its birth more than 13 billion years ago. Their orbits stretch far beyond the disk, moving through the halo like relics of a forgotten era. From the outside, the young Milky Way would have looked nothing like the graceful spiral we know now. It was rough, uneven, full of collisions and streams. Its shape was being carved by gravity, impact by impact, layer by layer. But over billions of years, this storm of merging galaxies settled into a single massive structure. A rotating disk, a central bulge, and a halo of ancient stars began to take shape. The Milky Way had been born not in a single moment, but through a long, violent, and beautiful process of cosmic construction. Even today, traces of those early days remain written across the sky. Tidal streams arc through the halo, globular clusters trace ancient paths, and the disk itself still bears scars from those collisions, silent reminders of the galaxy's turbulent childhood. This is where the story begins. Before the sun, before the earth, before life, the Milky Way was already spinning in the dark. From a distance, the Milky Way looks like a smooth, flat disk of stars. But that image is an illusion. At its outer edges, the disk bends and twists like a soft sheet caught in a gentle wind. This warp is one of the most fascinating clues to the galaxy's dynamic history. The warp is not a small feature. It rises thousands of light years above and below the main galactic plane, curving like the brim of a spinning hat. If you could look down from far above the galaxy, you would see its outer disk ripple upward on one side and downward on the other. It is a quiet but powerful reminder that the Milky Way is not rigid. It is flexible, alive, and constantly in motion. Scientists believe the warp was shaped by encounters with smaller galaxies that orbit the Milky Way. The most influential of these is the Large Magellanic Cloud, a bright satellite galaxy trailing streams of gas behind it. Its gravity tugs on the Milky Way's outer disk, slowly twisting the edges over billions of years. Other faint satellite galaxies, like invisible hands, pull and stretch the galactic plane in their own subtle ways. The dark matter halo also plays a role. Surrounding the galaxy like a vast invisible cocoon, this halo acts as a gravitational anchor. When the satellites orbit through it, their gravity disturbs the halo, and the halo in turn transfers that disturbance to the disk. This is why the warp is not a single clean curve. It ripples and shifts as if the galaxy were remembering every encounter it has ever had. Astronomers map the warp by studying neutral hydrogen gas at the outer rim of the galaxy. Unlike starlight, this gas can be traced far beyond the visible disk. Observations show the warp is asymmetric. It is higher on one side than the other, and it moves. It's not frozen in place. It slowly precesses like the wobble of a spinning top. This bending of the disk has consequences. It affects the orbits of stars and the flow of gas in the outer regions. It may influence how new stars form near the edges of the galaxy, and it provides a living record of the Milky Way's interactions with its neighbours. Every ripple carries a story, a gravitational handshake that happened long ago. Even our own sun is not in a perfectly flat plane. As the solar system moves through the disk, it too feels subtle, vertical motions. These oscillations are tiny compared to the grand sweep of the warp, but they remind us that nothing inside the Milky Way is truly fixed. Everything moves. Everything responds. The warp is not unique to our galaxy. Many spiral galaxies show similar twists at their edges, suggesting that interactions with companions and dark matter halos are common in cosmic evolution. But the Milky Way's warp is special to us because we live inside it. We don't see it directly. We discover it by carefully mapping the motions of stars and gas around us. The edges of the Milky Way are like the surface of a vast ocean stirred by distant tides. Quiet, slow and powerful, every galaxy is built on something invisible. Beneath the stars, beneath the glowing disk, beneath everything we can see, there is a hidden skeleton holding it all together. For the Milky Way, that skeleton is made of dark matter. Dark matter does not shine. It does not reflect light or block it. We can't photograph it, but it has mass, and mass means gravity. Long before the Milky Way took shape, clouds of dark matter formed the first structures in the universe. These invisible halos acted like scaffolding. Gas flowed into them, cooled and condensed into stars. Without that hidden foundation, no galaxy would exist at all. The Milky Way's dark matter halo is enormous. It extends far beyond the visible disk, stretching perhaps 300,000 light-years from the galactic center, more than 3 times the width of the spiral we can see. Most of the galaxy's mass is inside this halo, not in the stars or gas. The glowing disk is just a thin, fragile surface floating inside something far larger and heavier. We know this halo exists because of how stars move. Near the center of the galaxy, stars orbit quickly, that's expected. But out at the edge, where the visible mass thins out, stars should slow down. Instead, they keep moving at almost the same speed. Something unseen must be providing extra gravity. That something is dark matter. The shape of the halo is not fully known. It may be roughly spherical or slightly flattened, perhaps even twisted by ancient mergers. Satellite galaxies and long tidal streams of stars curve through it like glowing threads tracing its invisible pull. Every orbit, every ripple, every motion in the galaxy happens inside this silent structure. This dark skeleton also affects how the galaxy evolves. It stabilizes the spinning disk, preventing it from tearing itself apart. It guides the motion of satellite galaxies and the flow of gas around the Milky Way. And during its early years, it was this skeleton that gathered the small fragments that merged to form the galaxy's core. Astronomers detect dark matter through its gravitational influence, not by direct observation. They map the halo by tracking stellar velocities, satellite orbits, and the bending of light from distant galaxies. Bit by bit, these measurements reveal the shape of something we can never see directly. In many ways, the Milky Way is just the bright skin of a much larger creature. What we call the galaxy is only the part that glows. Its true body is dark and silent, wrapped around everything like an invisible cocoon. Even when the last stars burn out billions of years from now, the dark matter skeleton will remain unchanged and unseen, the ghostly frame of a galaxy long gone. Long before the Milky Way became the graceful spiral we see today, the first stars were already gathering into dense ancient families. These families are still here orbiting quietly in the galaxy's halo. They are called globular clusters, some of the oldest surviving structures in the entire universe. A globular cluster is a nearly perfect sphere of stars packed so tightly that hundreds of thousands of suns can fit within just a few dozen light years. The stars inside are old, born more than 10 billion years ago, at a time when the galaxy itself was still taking shape. Unlike the young clusters we find in the spiral arms, these globular clusters are cosmic fossils. They orbit far above and below the galactic disk, tracing long tilted paths through the halo. These orbits are not random. Many of them carry the fingerprints of ancient mergers, collisions between the Milky Way and smaller galaxies that were absorbed long ago. When those galaxies were torn apart, their star clusters remained still moving through space like silent witnesses to a violent past. The stars inside globular clusters are mostly small and long-lived. They shine with a steady faint light, untouched by the bursts of star formation that shape the rest of the galaxy. Their chemical makeup is different too. They contain far fewer heavy elements than the Sun. This tells astronomers they formed early, before generations of supernovae enriched the galaxy with new materials. Globular clusters are incredibly stable. Their intense gravitational binding allows them to survive for billions of years, resisting the tidal forces that tear other star groups apart. Many orbit the Milky Way's center once every few 100 million years, passing through the galactic plane like ancient comets. Each passage distorts their shape slightly, but they endure. Astronomers study these clusters not only for their beauty, but because they are time capsules. By measuring the age of their stars, scientists can estimate the minimum age of the galaxy itself. Some globular clusters are older than the Milky Way's disk, meaning they existed before the spiral structure fully formed. They are pieces of the galaxy's original building blocks still moving through the present. There are more than 150 known globular clusters orbiting the Milky Way, and there may be many more hidden behind dust and gas. Each cluster is a relic of a different era, a fragment of the galaxy's childhood. When we look up at the night sky, most of these clusters are too faint to see with the naked eye, but through a telescope they reveal breathtaking views, glittering spheres of stars suspended in darkness, unchanged for billions of years. The Milky Way has grown, evolved, and reshaped itself countless times since they formed. But the clusters remain. They are the oldest voices in the galactic chorus, still singing the song of the galaxy's beginning. At the center of the Milky Way, hidden behind curtains of dust and gas, lies a structure that quietly shapes the galaxy's destiny. It is the galactic bar, a long, bright spine of stars stretching across the core like a glowing bridge. It is not just a feature of the center. It is the engine that drives the galaxy's rhythm. The bar is made of billions of stars moving in elongated orbits. Together they form an elegant structure about 27,000 light-years long. This stellar river rotates slowly, roughly once every 100 million years. Its gravitational pull is powerful. It stirs the galaxy's inner disk, pushes gas toward the center, and sends ripples outward into the spiral arms. If the spiral arms are the graceful curves of the Milky Way, the bar is its backbone. It sets the pattern speed of the spiral structure, guiding how density waves travel through the disk. These waves create the bright star-forming regions we see in the arms. Without the bar's influence, the spiral pattern would lose its coherence and gradually blur into disorder. Gas flowing toward the bar does not simply fall into the core. It spirals inward, compressed by gravity, triggering bursts of star formation near the centre. Over billions of years, this slow but steady flow has built the galaxy's bulge and fed the activity surrounding Sagittarius A. The bar is like a gravitational funnel steering the Milky Way's lifeblood toward its heart. Astronomers discovered the bar by mapping the motions of stars and gas in the inner galaxy. The stars there don't follow simple circular orbits. Their paths align with the shape of a rotating bar. Infrared telescopes, which can peer through the dust, confirm the structure's existence and revealed its tilted orientation relative to our position in the disk. Bars are common among spiral galaxies, but each one tells a different story. Some grow longer and stronger over time, influencing how their host galaxies evolve. In the Milky Way, the bar likely formed a few billion years after the galaxy's birth as instabilities in the disk and gravitational tugs from smaller galaxies shape the inner region. Even though we live far from the centre, the bar affects us. The spiral arms that our sun drifts through, the flow of gas in the disk, and the timing of star formation across the galaxy are all linked to its slow rotation. It is a silent metronome setting the pace for the Milky Way's cosmic dance. If we could look down on the galaxy from above, we would see the bar shining across the core with spiral arms unfurling from its ends like ribbons in a gentle wind. It is not just a structure at the centre, it is the heartbeat of the galaxy. Surrounding the galactic bar like a glowing core is the central bulge, a dense spheroidal concentration of ancient stars. This is the oldest and most crowded region of the Milky Way, a place where gravity dominates, and the galaxy's history is written in starlight. The bulge spans tens of thousands of light years, forming a thick rounded structure at the centre of the disk. Unlike the graceful spiral arms, the bulge is chaotic. Stars move along random intersecting paths rather than neat circular orbits. The density here is extreme tens to hundreds of times greater than in the Sun's neighbourhood. If you stood on a planet inside the bulge, the night sky would be blinding, filled with countless stars blazing in every direction. Most of the stars in the bulge are old, formed more than 10 billion years ago during the early and violent stages of the galaxy's life. Their chemical composition is different from that of younger stars in the disk. Many have low metallicity, meaning they formed before supernovae enriched the galaxy with heavy elements. But the bulge is not entirely ancient. Some stars are younger, born from gas funneled inward by the galactic bar, showing that this region continues to evolve even now. The shape of the bulge is not a perfect sphere. It is stretched into a subtle peanut or X shape sculpted by the slow rotation of the bar. Over billions of years, stars have reorganized themselves into this distinctive structure, a fingerprint of the galaxy's inner dynamics. This shape is best seen in infrared light, which can pierce the dense dust clouds that hide the central regions from visible telescopes. The bulge plays a crucial role in the galaxy's balance. Its mass, hundreds of billions of suns, anchors the inner disk and stabilizes the rotation of the bar. It also surrounds Sagittarius A, the supermassive black hole at the very core. The stars here move at breathtaking speeds, responding to the intense gravity at the center. For astronomers, the bulge is like a time machine. By studying its stars, they can trace the earliest chapters of the Milky Way story. Many of these stars formed before the disk and spiral arms fully emerged. Their motions still carry the echoes of ancient mergers and gravitational turbulence. Observing the bulge is difficult because Earth lies inside the dusty disk. But infrared surveys and space telescopes have revealed its detailed structure, turning what was once a mysterious blur into a clear map of the galaxy's heart. The bulge is the memory of the Milky Way, dense, old and unshakable. While the spiral arms shimmer with young stars and dust, the bulge endures quietly, a heavy core at the centre of a spinning disk. When most people imagine a galaxy, they picture its spiral arms, sweeping curves of light reaching outward like vast ribbons of stars. In the Milky Way, these arms are its most recognisable feature, but despite their graceful appearance, they are not rigid structures. They are waves patterns of density moving through the disk. The Milky Way's spiral arms are regions where gas dust and stars are temporarily crowded together by gravitational effects. As material in the disk orbits the center, it moves in and out of these denser zones. When clouds of gas pass through a spiral arm, they slow down slightly, compress and collapse. This compression ignites bursts of star formation. The brightest, hottest and youngest stars appear right in the arms, lighting them up like glowing trails through the dark. The spiral arms do not rotate at the same speed as individual stars. Stars move faster than the pattern itself, drifting in and out over time. This is why the arms are often compared to traffic jams on a highway. The cars move, but the dense region stays in place and travels as a wave. Our galaxy has several major arms, including the Sagittarius and Perseus arms, along with smaller structures like the Orion spur, the quiet side branch where our sun resides. Each arm stretches for tens of thousands of light years, curving gently as it wraps around the galactic center. The arms are shaped and maintained by a combination of forces: the galaxy's rotation, the influence of the galactic bar, and the distribution of mass in the disk and halo. The bar plays a special role. As it rotates, it sends out waves that ripple through the disk, creating the spiral pattern. This is why the Milky Way's arms begin at the ends of the bar. The two structures are connected like gears in a cosmic machine. The spiral arms are not smooth. They are filled with knots, branches and spurs, regions where star formation is particularly intense. Clusters of massive stars illuminate these pockets, while shock waves from supernovae shape the surrounding gas. This restless activity is what makes the arms look so vibrant. For astronomers, mapping the spiral arms from inside the galaxy is a challenge. We can't take a picture of the Milky Way from above, so scientists use radio and infrared observations to trace clouds of hydrogen star clusters and mazes. By combining these maps, they reconstruct the spiral structure, revealing the arms as dynamic, ever-changing patterns rather than fixed roads. The arms are the places where the galaxy is most alive. Stars are born here, massive stars explode here, and the cycle of creation and destruction never stops. Without these density waves, the Milky Way would be a more static, less vibrant place, a disk without a heartbeat. When we look up at the Milky Way's glowing band across the night sky, we're looking along one of these spiral arms from the inside. It is a view from within a grand rotating wave of stars. Surrounding the flat glowing disk of the Milky Way is a vast, almost invisible structure, the galactic halo. It extends far beyond the spiral arms, stretching hundreds of thousands of light years into space. Though faint and diffuse, the halo is essential to the galaxy's stability and history. It is the silent, ancient envelope in which everything else floats. The halo is not made of a single component. It contains three main elements: ancient stars, globular clusters, and a vast sphere of dark matter. While the disk is thin and bright, the halo is nearly spherical, reaching at least 300,000 light-years across. Most of the galaxy's total mass lies here, hidden in its dark matter skeleton, which we already uncovered earlier. The stars in the halo are old and sparse, spread over enormous distances. Unlike the stars in the disk, they do not follow the galaxy's rotation. Their orbits are tilted, stretched, and irregular, fossil traces of ancient collisions. Many of these stars came from smaller galaxies that merged with the Milky Way long ago, torn apart and scattered into long, faint streams. These stellar streams still drift through the halo like ghostly rivers. Globular clusters also live here, orbiting high above and below the disk. Their steady paths cut through the halo like clockwork, marking the structure's extent. Because these clusters are so old, they give astronomers clues about how the halo formed, likely through the slow accretion of smaller systems over billions of years. The halo is not completely empty of gas. It contains hot, thin plasma at temperatures of millions of degrees. This gas is part of the circumgalactic medium, a vast reservoir that exchanges material with the disk. Gas from supernovae rises into the halo, cools and falls back down, fueling new generations of stars. At the same time, the halo may also catch material from intergalactic space, feeding the galaxy from the outside. Its role is more than just structural. The halo acts as a gravitational anchor, holding the disk in place and stabilizing its rotation. Without this massive invisible shell, the Milky Way's delicate spiral structure would warp and unravel much more quickly. The halo also protects the galaxy in a way its dark matter mass slows down encounters with satellite galaxies and absorbs part of their energy during mergers. For astronomers, mapping the halo is like exploring an ancient ruin hidden in fog. We can't see it directly, but we detect it through stellar motions, gravitational effects, and the faint X-ray glow of its hot gas. Surveys like Gaia have revealed stream shells and substructures inside the halo, a clear sign that it is not smooth, but shaped by a long history of collisions. The halo is the galaxy's quiet outer skin. It doesn't shine like the spiral arms or flare with star formation, but it carries the memory of everything that ever collided with the Milky Way. It is both the galaxy's oldest feature and its greatest shield. The Milky Way is a grand spiral galaxy with massive arms sweeping outward from the central bar. But the Sun doesn't live in one of those main arms. It resides in a quieter place, a smaller branch called the Orion Spur. This narrow structure is a kind of galactic side street tucked between two major arms, Sagittarius and Perseus. The Orion Spur stretches for several thousand light years, forming a bridge between its larger neighbours. It is not as dense or star-rich as the main arms, but it contains enough gas and dust to host active star formation. Here within this modest structure, the Sun was born about 6 billion years ago. Our position in the galaxy is significant. The Sun orbits about 27,000 light-years from the galactic centre, roughly halfway between the crowded core and the outer edge of the disk. This location gives us a stable cosmic environment. Closer to the centre, radiation and supernova rates are higher, while farther out star formation slows and resources become sparse. The Orion Spur sits in a kind of galactic Goldilocks zone, not too violent, not too empty. The spur is oriented along the plane of the disk, and when we look up at the night sky, the glowing band of the Milky Way is our view along this structure. Every bright star we can see with the naked eye belongs to our local spur or its immediate surroundings. We're not looking at the entire galaxy. We're looking through a narrow corridor of stars, gas and dust that happens to be our home. The Sun moves through the Orion Spur at about 220 kilometers per second, completing a full orbit around the galactic center every 230 million years. During this long journey, the solar system slowly drifts relative to the surrounding stars, and the spur itself may shift shape over cosmic time. Spurs are not permanent structures. They can grow, merge with larger arms, or fade as density waves evolve. One of the unique aspects of the Orion Spur is its proximity to active star-forming regions. The Orion Nebula, for example, is part of a massive molecular cloud complex nearby. This region is producing new generations of stars right now, proof that even a modest galactic spur can be vibrant. Our location also gives us a clear window into the structure of the Milky Way. Because we're not buried deep inside a main arm, astronomers can observe the sky with less interference from dust and dense star fields. This clearer vantage point has been essential for mapping the rest of the galaxy and discovering its spiral pattern. The Orion Spur is often overlooked compared to the galaxy's grander structures, but for us it is everything. It is where the Sun formed, where Earth was born, and where all of human history has unfolded. In a galaxy of hundreds of billions of stars, we occupy a small, quiet lane, and that may be why we're here at all. The Sun does not stand still. Like every other star in the Milky Way, it follows a long, complex orbit shaped by the galaxy's gravity. Our solar system is not anchored to a fixed point. It is part of a vast, swirling motion that has lasted for billions of years and will continue long after we're gone. The Sun orbits the galactic center at an average speed of about 220 kilometers per second, One full revolution takes roughly 230 million years a galactic year. This means that since its birth, the Sun has completed more than 20 full orbits around the centre. When it last passed through this region of its orbit, Earth's continents were arranged in a supercontinent called Pangaea, and dinosaurs were beginning to rule the planet. The orbit is not a perfect circle. It is slightly elliptical, and the Sun oscillates gently up and down through the galactic plane as it moves forward. This vertical motion happens over tens of millions of years like a slow wave. The causes of this oscillation lie in the gravitational pull of the disk, the spiral arms, and the dark matter halo surrounding the galaxy. These oscillations may have consequences. Some scientists have proposed that the Sun's periodic passages through denser regions of the disk could influence the solar system, for example, by slightly increasing the flux of comets from the Oort cloud. Over very long timescales, the galaxy itself becomes part of Earth's natural cycles. The Sun does not travel alone. It moves with a local flow of stars called the local standard of rest, which orbits the galaxy in roughly the same direction and speed. But each star also has its own peculiar motion, small deviations that make stellar paths diverge slowly over time. This is why the stars we see in the night sky today will form a very different pattern millions of years from now. As the Sun moves, it occasionally drifts closer to or farther from spiral arms. The Orion spur itself may not be permanent. It could merge with one of the larger arms or dissolve into the background disk. Over hundreds of millions of years, this slow drift exposes the solar system to slightly different galactic environments. Our cosmic address may change, but the journey continues. This orbit is stable but not immutable. Encounters with giant molecular clouds, spiral arm passages, and the gravitational influence of the Large Magellanic Cloud and other satellite galaxies can subtly reshape the Sun's path. The Milky Way is a dynamic system, and everything within it, even stars like the Sun, responds to that movement. When we look at the stars, we rarely think of them as travellers. But the truth is, we're all on a grand voyage. Right now, the entire solar system is sailing through the galaxy, following a path carved by gravity nearly 5 billion years ago. And this journey's far from over. The Milky Way is home to hundreds of billions of stars, a vast and diverse population, spanning every stage of stellar evolution. These stars are not randomly distributed. They belong to different groups, each with its own history, chemical makeup, and role in the galaxy's structure. Together they form a living record of how the Milky Way grew and changed over time. Astronomers often divide stars into two broad populations. Population I stars are young and rich in heavy elements heavier than hydrogen and helium. These stars are concentrated in the spiral arms and disk where new stars continue to form. The Sun is one of them. It was born from material enriched by countless earlier generations of stars. Population II stars are much older and poorer in heavy elements. Most of them live in the halo and bulge. They formed when the universe was still young, before supernovae had filled the galaxy with metals. These stars act as time capsules, preserving chemical fingerprints from the galaxy's earliest days. Some astronomers also use the term population III for the very first stars in the universe, massive metal-free giants that lived and died long before the Milky Way fully formed. None of these stars are thought to remain today, but their existence is written into the chemical composition of the oldest population II stars. The age of a star and its chemical composition are closely linked. Heavy elements are created inside stars and spread through space when those stars die. Each new generation of stars contains more of these elements than the one before. This is why stars in the disk like the Sun have planets rich in metals, and why ancient halo stars tend to lack them. The distribution of these stellar populations is not uniform. The disk contains young and middle-aged stars orbiting in orderly, almost circular paths. The halo, by contrast, is home to ancient stars on random elongated orbits. The bulge is dense with old stars, but also includes younger ones funneled in by the bar. By studying these distributions, astronomers can reconstruct how the galaxy grew. From a chaotic past of mergers to the structured spiral we see today, star mass also shapes the galaxy's story. Most stars are small faint red dwarfs that will live for trillions of years. A smaller number are like the Sun medium mass burning steadily for billions of years, and a rare few are massive blue giants that live fast and die young, seeding the galaxy with heavy elements when they explode. The mixture of stellar populations is not static. As stars age, die and are replaced, the character of the galaxy slowly changes. Over billions of years, the bright blue stars in the arms will disappear, leaving cooler, redder stars behind. In this way, the Milky Way evolves not only through mergers and structure, but through the slow aging of its stellar inhabitants. Every point of light in the night sky is part of this larger story. Some stars are young, still burning with the fuel of a recent birth. Others are ancient, shining with the same light that began when the galaxy itself was just forming. Together, they make up the living population of a galaxy in motion. When we look at the night sky, we often imagine stars as solitary beacons drifting alone through space. But in reality, most stars in the Milky Way are not alone. They live in pairs or larger groups bound together by gravity in intricate celestial dances. Binary and multiple star systems are the rule, not the exception. A binary star system consists of two stars orbiting a common center of mass. The stars may be similar in size or vastly different. Some pairs are wide, separated by hundreds or even thousands of astronomical units. Others are so close that their outer layers touch, or even merge, forming contact binaries. Their orbits can be stable for billions of years, shaped entirely by gravity's silent precision. In some systems, the stars take turns dominating the light we see. When one passes in front of the other, their combined brightness dips. This is how astronomers detect many binaries. In other cases, they reveal themselves through Doppler shifts in their spectra, tiny changes in wavelength that betray their orbital dance. Multiple star systems go beyond pairs. Some contain 3, 4, or even more stars locked together in complex gravitational hierarchies. In a triple system, for example, 2 stars may orbit each other closely while a third orbits farther out. These systems can be surprisingly stable if the distances and masses are just right. But small perturbations can also lead to chaos, sending one star drifting away into interstellar space. Binary and multiple stars play a major role in shaping the galaxy's evolution. When massive stars exist in pairs, they can exchange material as they age. One star may strip its companion, or they may merge, producing exotic objects like blue stragglers or even supernova explosions. These interactions enrich the surrounding interstellar medium with heavy elements, helping future generations of stars and planets to form. They also influence stellar death. A white dwarf in a binary system can siphon material from its companion until it reaches a critical mass, triggering a thermonuclear explosion, a type Ia supernova. These explosions are so uniform in brightness that astronomers use them to measure the expansion of the universe. For planets, binaries present both opportunities and challenges. Some planets orbit one star while feeling the distant tug of another. Others orbit both stars together in what are called circumbinary orbits. These systems can be stable, but their gravitational environments are complex. Whether such systems can host life depends on delicate orbital balances. The sheer abundance of binary and multiple star systems reshapes how we understand the galaxy. Our Sun, a single star, is actually in the minority. This makes our solar system somewhat unusual, though not unique. From wide pairs drifting peacefully through the disk to tight, violent mergers in the core binary, and multiple stars are everywhere. They are part of the galaxy's hidden machinery, shaping stellar evolution, forging heavy elements and sending ripples of energy through the interstellar medium. Every star has a story, and for most of them it's not a solo journey. It's a dance. Deep in the heart of the Milky Way lies a region unlike any other part of the galaxy. It is dense, chaotic, and brilliant with energy, the galactic center. This is where gravity dominates everything. Stars race through space at incredible speeds, clouds of gas twist and collide, and a supermassive black hole waits at the core. The galactic center sits about 27,000 light-years from the Sun, hidden behind thick curtains of interstellar dust. Visible light cannot penetrate this dusty barrier, which is why this region remained mysterious for centuries. Only with infrared and radio telescopes have astronomers been able to peel back the veil and see its true nature. The stellar density here is staggering. In just a single cubic light year, there can be more than 1,000 stars compared to only a fraction of one in our local neighborhood. Many of these stars are old and metal-rich, but there is also evidence of recent star formation. Massive hot short-lived stars orbit close to the center, some moving at thousands of kilometers per second. Their presence means that even in this extreme environment, the galaxy still creates new stars. The interstellar medium here is turbulent. Gas clouds are compressed and stretched by gravity-magnetic fields and shock waves. Supernova explosions stir the region, and powerful stellar winds carve channels through the gas. This chaotic motion creates some of the brightest radio and infrared emissions in the entire galaxy. This environment is not just shaped by stars. It is also dominated by Sagittarius A, the Milky Way's central black hole, which sits right at the core. Even when it is relatively quiet, its immense gravity sculpts the orbits of nearby stars and shapes the behavior of the surrounding gas. When it flares, it floods the region with X-rays and radio waves. Surrounding the central black hole is a cluster of some of the most massive stars in the galaxy. Many of these stars are arranged in a disk-like structure orbiting in near-perfect alignment. Others have random plunging orbits. Together, their movement provides astronomers with a natural laboratory for testing the laws of gravity under extreme conditions. The galactic center is also home to unique structures. Massive molecular clouds, supernova remnants, and threads of magnetic fields stretching for dozens of light-years. These filaments, glowing in radio wavelengths, hint at processes we still do not fully understand. Despite its violence, this region is surprisingly stable on large timescales. It has existed for billions of years, pulsing with energy but held together by gravity. For astronomers, it's a window into how galaxies behave at their cores. Not just ours, but spiral galaxies across the universe. We live far from this maelstrom in a quiet spur of the galactic disk. But the galactic center is the Milky Way's heart. Its gravity holds the galaxy together. Its history echoes through the disk, and its future will shape everything. At the exact center of the Milky Way sits one of the most extraordinary objects in the universe, Sagittarius A. It is a supermassive black hole weighing about 4 million times as much as the Sun compressed into a region no larger than our solar system. Though invisible to the human eye, its gravity rules the heart of the galaxy. Sagittarius A does not shine like a star. Instead, its presence is revealed through the motion of everything around it. Nearby stars whip around it at breathtaking speeds, some completing an orbit in just a few years. Hot gas swirls in a violent accretion flow, producing X-rays and radio waves that escape into space. Even when it's quiet, Sagittarius A leaves an unmistakable gravitational imprint. For decades, astronomers suspected a massive object lurked at the galactic center. The breakthrough came when teams began tracking the orbits of individual stars near the core using high-resolution infrared telescopes. These stars moved in tight, fast orbits around an unseen point. The only explanation consistent with the data was a supermassive black hole. One star in particular, known as S2, became the most important test subject. It orbits Sagittarius A every 16 years, passing astonishingly close to the black hole at a speed of thousands of kilometers per second. By precisely measuring S2's path, scientists confirmed the black hole's mass and detected effects predicted by general relativity, including the bending of light and the precession of its orbit. Sagittarius A is not currently very active. It accretes matter, slowly producing only modest radiation compared to the blazing centers of some distant galaxies. But this wasn't always the case. Evidence suggests it was much more energetic in the past, launching powerful outflows that carved giant bubbles into the galaxy's halo. Those relics are still visible today. The Event Horizon Telescope, a network of radio telescopes around the world, has even imaged the region immediately surrounding Sagittarius A, capturing a glowing ring of hot gas swirling around its event horizon. This achievement marked the first direct glimpse of our galaxy's central black hole and confirmed decades of indirect evidence. The black hole itself is silent. It does not pull everything in like a cosmic vacuum cleaner. Only material that strays too close crosses the event horizon, disappearing forever. Most stars and gas in the galactic center orbit safely at a distance held in place by its gravity rather than consumed by it. Sagittarius A is the anchor of the Milky Way. It shapes the motions of stars near the core, influences how gas flows inward, and may even trigger star formation through its outbursts. It is not just a passive mass at the center. It is the hidden engine at the heart of the galaxy. When we look toward the constellation Sagittarius, we are looking toward this invisible giant. It has been here since the galaxy's youth, and it will remain long after the stars have faded. Some of the most precise tests of gravity in the entire universe take place just a few light days from Sagittarius A. There, a single star, S2 star, traces an extraordinary path through space, offering a direct window into the laws of nature near a supermassive black hole. S2 is a young, hot, massive star about 15 times the mass of the Sun. It follows a long elliptical orbit around Sagittarius A, reaching speeds of more than 7,000 kilometers per second at its closest approach. That's fast enough to travel from Earth to the Moon in less than a minute. Its orbit takes just 16 years to complete a blink of an eye on cosmic timescales. Astronomers began carefully tracking S2 in the 1990s, using infrared telescopes capable of piercing through the dusty veil that hides the galactic center. Over decades, they mapped every twist and turn of its orbit with extraordinary precision. What they found was the clearest evidence yet for the existence of a supermassive black hole at the Milky Way's core. S2 moves under the gravitational pull of Sagittarius A ER, and the way it does so matches the predictions of general relativity almost perfectly. As it swings past its closest point just 17 light hours from the black hole, its light is stretched to longer wavelengths by gravitational redshift, exactly as Einstein's theory predicts. No other explanation fits the data, but the star does more than confirm the black hole's presence. Its orbit also reveals the details of space-time around it. The shape of the path is not a perfect ellipse. It processes meaning. The point of closest approach slowly rotates over time. This subtle effect, called Schwarzschild precession, is a direct consequence of curved space-time near a massive object. Astronomers have measured it precisely, providing one of the strongest tests of Einstein's theory outside the solar system. No star has been observed orbiting so close to a supermassive black hole with such clarity. Future observations may detect even more subtle effects, such as frame dragging, the twisting of space-time by a rotating black hole. If Sagittarius A spins fast enough, its rotation could slightly alter the orbits of nearby stars. S2 is not alone. Other stars also orbit the galactic center, but none offer such a clean, well-measured test. In many ways, S2 has become a natural laboratory for fundamental physics, a cosmic probe placed right next to a 4 million solar mass black hole. This research has reshaped our understanding of both the Milky Way and gravity itself. It confirms that black holes behave as predicted and opens the door to future experiments that may reveal deviations from current theories. When astronomers point their telescopes toward the heart of the galaxy, they're not just watching a star. They're watching the fabric of space-time bend and twist in real time, a silent demonstration of the universe's most powerful law, High above and below the glowing disk of the Milky Way, two colossal structures rise like ghostly towers. They are called Fermi bubbles, immense lobes of high-energy particles and radiation, each stretching about 25,000 light-years from the galactic center. Their existence reveals a hidden chapter in the history of our galaxy, a time when the core was far more violent than it is today. The Fermi bubbles were discovered in 2010 by the Fermi Gamma Ray Space Telescope. Astronomers were mapping the sky in gamma rays when they noticed two huge symmetrical regions of excess emission extending above and below the galactic plane. These structures are invisible to the naked eye, but they glow brightly in high-energy light, marking a powerful outburst in the past. Their sharp edges and smooth surfaces suggest that they formed quickly, not through slow processes. The most likely explanation is a massive event at the galactic center a few million years ago, perhaps an energetic feeding episode of Sagittarius A. When supermassive black holes accrete large amounts of gas, they can launch jets or winds that blow material far into their galaxies. The Fermi bubbles are thought to be the fossil record of just such an outburst. Each bubble is filled with extremely hot gas, fast-moving particles and magnetic fields. They extend far into the galactic halo, dwarfing the visible disk. If we could see them with our eyes, they would dominate the night sky, arching high above the Milky Way's plane. But Sagittarius A is quiet now. The outburst that created the bubbles ended long ago, leaving behind this ghostly imprint. By studying the structure and energy of the bubbles, astronomers can estimate when the event occurred, probably between 2 and 6 million years ago, around the time early human ancestors were walking the Earth. The bubbles are not static. Observations in multiple wavelengths, gamma rays, X-rays and radio show that they are still evolving. Shock fronts at their edges indicate that hot gas is still expanding, though more slowly now. Their interiors contain cosmic rays, charged particles moving at nearly the speed of light, trapped and guided by magnetic fields. The Fermi bubbles are a reminder that the Milky Way's core is not always calm. For most of its recent history, Sagittarius A has been relatively quiet, accreting very little gas. But in the past, it behaved more like an active galactic nucleus, briefly lighting up the galaxy with energy powerful enough to reshape the halo. Similar bubbles and outflows have been observed in other galaxies, but finding them here in our own is different. It means the Milky Way is not just a passive spiral. It has a dramatic, explosive history and may erupt again in the distant future. These two giant lobes are silent now, but they are proof that the galaxy's heart can awaken. Between the bright stars of the lies, something far more subtle but just as important. A vast ocean of dust and gas. It is thin, cold, and almost invisible, yet it is the raw material from which every new star and planet is born. This is the breathing system of the galaxy. The interstellar medium fills the space between stars with an ever-shifting mixture of hydrogen, helium trace elements, and tiny dust grains. Though the average density is less than 1 atom per cubic centimetre, the Milky Way contains billions of solar masses of this material spread across its disk. It is both a graveyard for old stars and a nursery for new ones. Much of the gas is hydrogen, the simplest and most abundant element in the universe. In some regions, it exists as single atoms forming diffuse clouds that stretch for hundreds of light years. In others, it combines into molecules, creating dense pockets called these clouds, are where gravity begins to take over, pulling gas together until stars are born. Dust plays a crucial role in this process. These tiny grains, composed of carbon silicates and ice, absorb and scatter light, shaping how we see the galaxy. They shield delicate molecules from ultraviolet radiation, allowing them to survive and accumulate. Without dust, molecular clouds would quickly evaporate under the harsh glow of nearby stars. The dust is also the reason the Milky Way's plane appears as a dark mottled band in the night sky. It blocks visible light from distant stars, creating the familiar pattern of glowing regions and dark rifts. Yet in infrared wavelengths, the same regions blaze with hidden energy. revealing dense clusters and star-forming cores. This dust is not permanent. It is created and destroyed constantly. When stars die, especially, and they release heavy elements and dust grains into space, these grains drift through the galaxy, clumping together in new clouds and eventually becoming part of new generations of stars and planets. Every carbon atom in your body was once part of this cosmic cycle. The interstellar medium is not still. It moves in great currents and flows stirred by supernova shocks and stellar winds. Hot ionized gas rises into the galactic helocools and then falls back toward the disk, a process known as This cycle regulates star formation and recycles matter throughout the galaxy, maintaining its long-term balance. From a distance, the Milky Way looks serene, its arms glowing softly in starlight. But within those arms lies a dynamic ecosystem of gas and dust, forming collapsing, heating, cooling, and renewing itself across billions of years. When we look up and see the hazy river of light cutting across the sky, we are not just seeing stars, we are seeing the living body of our galaxy, the dust between the stars that makes everything possible. Every star in the Milky Way, including the Sun, began as a cloud of cold gas and dust floating silently between other stars. In the darkness of these molecular clouds, gravity slowly works its patient magic, turning diffuse material into brilliant spheres of light. Star formation is not a sudden event. It is a slow, intricate process that unfolds over millions of years. It begins when parts of a molecular cloud become unstable, often triggered by a shock wave from a nearby supernova or the gravitational pull of passing material. Once a region becomes dense enough, gravity overcomes the internal pressure of the gas, causing it to collapse inward. As the cloud contracts, it fragments into smaller clumps, each destined to become a star. At the heart of each collapsing clump, gas and dust spiral inward, forming a dense core that heats up as gravitational energy is converted into thermal energy. Eventually, the temperature and pressure become high enough to ignite nuclear fusion hydrogen. Atoms fuse into helium, releasing energy. A new star is born. Around this young star, a disk of leftover material forms. These disks are the birthplaces of planets, moons, and asteroids. Over time, dust grains collide and stick together, forming larger bodies through accretion. This is how entire solar systems emerge from what was once just a patch of cold gas drifting in space. Star formation is not evenly distributed throughout the Milky Way. It happens mostly in the spiral arms where density waves compress gas and create long chains of molecular clouds. These clouds can stretch for hundreds of light years and contain enough material to form thousands of stars. Regions like the Orion Nebula give us a glimpse into this process. They're active nurseries where new stars blaze into life while still surrounded by the clouds that created them. Most stars are born in clusters, not isolation. Over time, many of these clusters disperse, releasing their stars into the galaxy's disk. Our Sun likely formed in such a cluster more than 4 billion years ago. Though its siblings have long since drifted away, they still orbit the galactic center alongside us. Not every clump becomes a star. Some are too small to ignite fusion and become brown dwarfs, objects that blur the line between star and planet. Others may be torn apart by turbulence before they can fully collapse. Star formation is a competitive process shaped by both gravity and chance. The balance between starbirth and death defines the life cycle of the Milky Way. As long as molecular clouds exist and gas continues to flow through the spiral arms, new stars will keep forming. This quiet, ongoing process gives the galaxy its light, its structure, and its future. Every star that has ever existed and every star that ever will begins in the soft darkness of a molecular cloud. Every star in the Milky Way is born with a clock. Some live for trillions of years, others for only a few million. But no star lasts forever. When their fuel runs out, stars die. And in doing so, they return their matter to the galaxy, feeding the cycle that gives rise to new generations. Stellar death is not just an ending. It is the mechanism that keeps the galaxy alive. A star's fate depends on its mass. Small stars like sun-like stars or smaller in their lives quietly. After billions of years, they expand into red giants shedding their outer layers into space. These layers drift away, forming delicate shells of glowing gas called planetary nebulae. What remains at the core is a hot, dense remnant, a white dwarf that will slowly cool for billions of years. More massive stars follow a much more violent path. They burn through their fuel quickly, and when their cores can no longer sustain, fusion gravity takes over. The star collapses in a fraction of a second and then rebounds in a catastrophic supernova explosion. This event blasts heavy elements, iron, calcium, gold, uranium out into space, enriching the surrounding interstellar medium. These are the elements that later form planets, oceans, and life itself. The cores of these massive stars may become neutron stars or black holes depending on their mass. These compact objects linger long after their parent stars have vanished, orbiting silently or drifting through the galaxy. Some become part of binary systems generating bursts of X-rays, or even gravitational waves when they collide. Supernovae do more than create heavy elements. Their shock waves sweep through space, compressing nearby clouds of gas and triggering new rounds of star formation. In this way, the death of one generation of stars gives birth to the next. It is one of the fundamental recycling mechanisms that keeps the Milky Way evolving over billions of years. Not all stellar deaths are explosive. Over immense timescales, even white dwarfs will cool and fade into black dwarfs, and low-mass red dwarfs will slowly exhaust their hydrogen fuel. These quiet endings will dominate the far future of the galaxy when star formation slows and the spiral arms fade. This galactic recycling process is one of the reasons the chemical makeup of stars changes over time. The earlier stars were made of hydrogen and helium alone. Each generation added heavier elements, so stars like the Sun contain the remnants of countless supernovae and dying stars. We are literally built from their ashes. Every atom in your body, carbon, oxygen, calcium, iron, was forged in the heart of a star and scattered into space when that star died. The galaxy is not just a collection of stars. It is a continuous cycle of birth, death, and renewal stretching across billions of years. In the Milky Way, endings and beginnings are not separate. They are the same event seen from two different sides. Not every star in the Milky Way follows a gentle orbit around the galactic center. A rare few are moving so fast that they can break free, entirely escaping the galaxy's gravitational grip. These are hypervelocity stars, cosmic runaways traveling at hundreds or even thousands of kilometers per second. Most stars orbit at roughly 220 kilometers per second bound securely to the Milky Way, but hypervelocity stars can reach speeds exceeding 1,000 kilometers per second. At those speeds, they are no longer merely circling the galaxy, they are leaving it behind. Once a star crosses the galaxy's escape velocity, nothing can pull it back. It becomes a traveller through intergalactic space. The first hypervelocity star was discovered in 2005. Since then, astronomers have found more, each one offering clues to powerful forces at work in the galaxy. One of the main mechanisms that creates them involves Sagittarius A. When a binary star system ventures too close to the supermassive black hole at the centre, tidal forces can tear the pair apart. One star is captured into orbit while the other is slingshot outward at incredible speed like a stone from a cosmic catapult. This process, known as the Hill's mechanism, can accelerate stars to velocities high enough to escape the Milky Way entirely. The ejected star races outward through the halo, carrying with it a record of the encounter written into its trajectory. Not all hypervelocity stars come from the galactic center. Some may be flung outward during close interactions between massive star clusters, or from supernova explosions in binary systems. In these cases, the surviving companion star is hurled into space when its partner explodes, leaving it to wander alone. These stars are difficult to find because they are rare and fast. Many are hot massive stars that shine brightly but live short lives. Others are older and fainter, making them harder to detect. Surveys like ESA's Gaia have revolutionized the search by precisely measuring stellar positions and motions across the entire sky, revealing candidates racing away from the disk. Hypervelocity stars are more than curiosities. They provide valuable information about the Milky Way's gravitational field, the mass of its dark matter halo, and the dynamics near its central black hole. By tracing their paths backward, astronomers can reconstruct where and how they were launched, turning each runaway into a data point in a much larger story. One day these stars will drift into intergalactic darkness, carrying with them the chemical signatures of the Milky Way. Long after they leave the disk behind, they will remain witnesses to its existence, crossing the cold void between galaxies. The galaxy is not a closed system. It is constantly gaining and losing matter, and hypervelocity stars are one of the clearest signs that even the Milky Way cannot hold on to everything it creates. When viewed from afar, the Milky Way might look like a smooth, flat spiral disk, but in reality its outer regions are bent and twisted like the brim of a warped hat. This subtle but remarkable shape is known as the galactic warp, and it's one of the most striking signs that the Milky Way is not a static structure. It's alive, bending, twisting, and moving through space. The warp begins beyond the Sun's orbit in the outer disk of the galaxy. Instead of lying in a flat plane, the disk curves upward on one side and downward on the other, like a gentle wave frozen in space. This distortion involves not just stars but also the immense reservoir of gas in the outer disk, which extends far beyond the bright spiral arms. For decades, astronomers debated what caused the warp. Today, the leading explanations point to a combination of gravitational influences. One major factor is the interaction between the Milky Way and its satellite galaxies, such as the Large Magellanic Cloud. As these companions orbit and tug on the Milky Way's outer regions, they can tilt and twist the disk. The dark matter halo surrounding the galaxy may also play a role, subtly shifting and pulling on the disk over billions of years. The warp isn't static. Observations show that it precesses meaning. It slowly rotates like a wobbling plate. This motion reflects the dynamic nature of the Milky Way structure and its interactions with its surroundings. The warp's shape and speed provide valuable clues about how mass is distributed throughout the galaxy, especially in its dark matter halo. Our own Sun lies well inside the flat part of the disk, so we don't feel the warp directly. But if we could look at the galaxy from far above, the bending would be clear. A massive stellar disk with edges gently curling upward and downward, tracing a cosmic wave. This shape is not unique to the Milky Way. Many other spiral galaxies show similar warps, which suggest they are a common consequence of gravitational interactions. The warp is just one part of the galaxy's larger motion. The Milky Way itself is not standing still in space. It moves through the local group at hundreds of kilometers per second, orbiting a common center of mass shared with Andromeda Galaxy and other smaller galaxies. Meanwhile, the entire local group drifts toward the Great Attractor, a massive concentration of galaxies and dark matter hundreds of millions of light-years away. All of this means that the Milky Way's shape and position are not fixed. They are part of a vast ongoing flow through the cosmos. The warp of its disk is one visible ripple in a much larger ocean of motion, the movement of an entire galaxy through time and space. Far from being a static pinwheel frozen in the sky, the Milky Way is a living structure bending under the influence of its neighbours, its dark halo and the invisible currents of the cosmic web. The Milky Way is not alone in space. It is surrounded by a swarm of smaller companions, faint dim galaxies bound to it by gravity. These satellite galaxy systems orbit the Milky Way like moons, around a planet quietly shaping its evolution. Though small compared to the main galaxy, their influence is profound. The most prominent of these companions are the Large Magellanic Cloud and Small Magellanic Cloud, visible from the southern hemisphere as two soft glowing patches of light. These irregular galaxies are close enough to be interacting with the Milky Way in real time. Their gravitational pull stirs the outer disk, helping to create the galactic warp. Streams of gas flow between these galaxies and the Milky Way, feeding its halo and potentially fueling future star formation. Beyond the Magellanic Clouds, astronomers have discovered dozens of faint dwarf spheroidal galaxies orbiting farther out. These galaxies are incredibly dim, containing only a few million stars, tiny compared to the hundreds of billions in the Milky Way. But many of them are rich in dark matter, making them valuable laboratories for studying how galaxies form and evolve. These satellite galaxies are not static ornaments. They are actively interacting with the Milky Way. Some are being slowly torn apart by tidal forces, leaving long streams of stars behind them. One of the most famous examples is the Sagittarius dwarf spheroidal galaxy, which is currently in the process of being absorbed. Its remnants form great arcs of stars wrapped around the Milky Way's halo like cosmic scars left by an ancient encounter. Such mergers have happened many times throughout the galaxy's history. In fact, a large fraction of the stars in the Milky Way's halo are thought to have originated in smaller galaxies that were devoured long ago. These events are part of the galaxy's natural growth, slowly increasing its mass over billions of years. Some satellite galaxies may eventually merge completely with the Milky Way. Others may remain in stable orbits for billions of years more. Their gravitational tugs influence the shape of the dark matter, halo the structure of the outer disk, and even the distribution of globular clusters. The discovery of new satellites is still ongoing. Modern sky surveys and instruments like Gaia continue to reveal faint hidden companions that were previously invisible. These small galaxies are like fossil fragments of the Milky Way's formation history, each carrying a piece of the past. When we picture the Milky Way, it's easy to imagine a single isolated spiral drifting through space. But in reality, it's more like a living archipelago, a large island surrounded by many smaller ones. And through their slow, silent interactions, these satellites are helping to shape the future of the galaxy itself. Far beyond the spiral arms of another giant galaxy is drawing closer. It shines faintly in our night sky as a small blur in the constellation Andromeda. But in reality, it is more than 2 million light-years away and roughly as massive as our own. The two galaxies are on a slow but inevitable collision course. Andromeda is approaching at about 110 kilometers per second. That might sound fast, but on cosmic scales it's a gentle drift. The two galaxies will meet in roughly 4 billion years, about the same time that begins to evolve into a. When they finally collide, it won't be an explosion or an instant impact. Instead, it will be a slow, graceful merger lasting several billion years. Because galaxies are mostly empty space, their stars will almost never collide directly. The distance between stars is simply too vast. Instead, the merger will unfold as a titanic gravitational dance. The disks of both galaxies will be stretched and twisted, their spiral arms shredded into long tidal streams. Massive clouds of gas will crash together, sparking bursts of star formation far brighter than anything seen in the Milky Way today. At the center of each galaxy lies a supermassive black hole in the Milky Way, and a much larger one in Andromeda. As the galaxies merge, these two black holes will spiral toward each other, eventually coalescing into an even larger black hole. The merger will release enormous amounts of energy in the form of ripples in space-time that will echo across the universe. For the stars, the outcome will depend on their positions. Some may be flung into intergalactic space, becoming rogue stars drifting between galaxies. Others will settle into new orbits as the merged system stabilizes. Over time, the chaotic structure will relax into a new form, a massive smooth often referred to as Milkomeda. Our Sun and its planets will likely survive the merger intact. Simulations show that while their orbits around the galactic center will change, the solar system itself will not be torn apart. Future observers, if any exist, will see the sky filled with billions of new stars as the two galaxies blend together. This event is not unique. Galaxy mergers are a natural part of cosmic evolution. The Milky Way itself was built from countless smaller collisions in the distant past. The upcoming merger with Andromeda is simply the next chapter in that long story, the moment when two great spirals become one. Long after the collision star formation will fade as the combined galaxy exhausts its gas. What remains will be a vast quiet sphere of aging stars orbiting a single massive black hole at its centre. When we look at Andromeda today, we're not just seeing a neighbouring galaxy, we are seeing our future. The Milky Way, like every galaxy, is not eternal. It is a living structure shaped by gravity time and the slow drift of matter through the universe. Its future is written not in sudden cataclysm, but in long, majestic transformations unfolding over billions of years. In roughly 4 billion years, the Milky Way will collide with the Andromeda Galaxy. This slow merger will transform both spirals into a single massive elliptical galaxy, often nicknamed Milkomeda. The graceful spiral arms will be stretched and torn apart, star clusters will be scattered, and their central black holes, Sagittarius A and Andromeda's much larger black hole, will merge into one even more massive engine at the centre. Star formation will surge during the early stages of the merger as gas clouds collide and compress. The night sky from a vantage point within the solar system will be filled with brilliant arcs of stars far denser and brighter than anything we see today. It will be a breathtaking era, but also a temporary one. As time passes, the combined galaxy will consume or expel its gas, and the pace of star birth will slow dramatically. Several billion years later, Milkomeda will settle into a smooth, rounded shape. Without spiral arms and fresh gas, it will be a quieter galaxy. The youngest, hottest stars will burn out, leaving behind a population dominated by long-lived red dwarfs and fading stellar remnants. The glow of the galaxy will gradually shift toward the red, a sign of aging on a cosmic scale. Beyond that, other fates await. The Large Magellanic Cloud and other satellites will likely be absorbed along the way. Milkomeda will continue to drift through the local group, which itself may eventually merge into a single giant elliptical galaxy. Trillions of years from now, when star formation has nearly ceased, the galaxy will enter its twilight era. Stellar remnants, white dwarfs, neutron stars and black holes will dominate the stellar population. The luminous spiral that defines the Milky Way today will be long gone. Even gravity's reach has limits. Over unimaginable timescales, encounters between stars will slowly scatter many systems away from the galaxy entirely. The supermassive black hole at the centre will remain surrounded by a dim, fading halo of ancient stars. This distant future is not tragic. It is the natural evolution of a galaxy. The Milky Way itself was born from collisions and will end as part of something larger, just as countless other galaxies have before it. When we look up at the Milky Way arching across the night sky, we are seeing only a single moment in its vast lifetime, a moment of youth filled with light, spiral arms and star formation. Long after this era has passed, its legacy will still drift through the universe as part of a larger whole. The Milky Way is just one galaxy among trillions woven into a structure so vast it defies ordinary imagination. This structure is the cosmic web, a colossal network of filaments and clusters that forms the skeleton of the universe. Like a single star in a galaxy, the Milky Way is only a tiny node in this immense cosmic tapestry. The cosmic web is made of dark matter gas and galaxies arranged in long filaments stretching hundreds of millions of light years. At the intersections of these filaments lie galaxy clusters and superclusters regions, where matter has gathered most densely since the beginning of cosmic time. Between the filaments are vast dark voids where very little exists. The Milky Way belongs to a small galaxy group known as the Local Group. This group is dominated by two giant spirals, the Milky Way and the Andromeda Galaxy, along with dozens of smaller satellite galaxies. The Local Group itself is part of a larger flow of matter toward the Virgo cluster, and beyond into a gravitational basin called the Laniakea supercluster. This entire region spans more than 500 million light-years. The The cosmic web is not static. Galaxies and clusters are slowly moving along its filaments, pulled by gravity toward denser regions. The Milky Way and Andromeda are part of this flow. Their future collision is just a local example of a universal process, structure forming as matter falls inward along the web's strands. Dark matter is the invisible scaffolding that holds this web together. Ordinary matter stars gas planets as makes up only a small fraction of the total mass. Without dark matter, the web would unravel. With it, it grows more structured over time. The Milky Way, like every galaxy, is embedded in one of these dark filaments, bound into the shape of the universe itself. On the largest scales, the cosmic web resembles a living network. Clusters act like glowing nodes. Filaments resemble bridges of light. And galaxies, each containing billions of stars, are the bright threads running through it. From far enough away, the Milky Way would appear not as a special place, but as a single luminous pearl on an infinite cosmic string. Billions of years in the future, as cosmic expansion accelerates galaxies outside our local supercluster, will drift beyond the cosmic event horizon. They will fade from view forever, leaving the descendants of the Milky Way isolated within a small island of the universe. But even then, the structure of the cosmic web will remain written into the motions of the galaxies we can still see. The Milky Way was born in this web shaped by it and will one day disappear into its quiet background. It is a single wave in the great ocean of cosmic structure. Billions of years from now, there will be no bright arch of the Milky Way stretching across the night sky. Its spiral arms will have faded, its star-forming regions will have gone quiet, and its shape will have merged into something new, part of a single, massive galaxy, born from the collision with the Andromeda Galaxy. But even then, the galaxy will remember. Its stars will still carry chemical fingerprints from the gas clouds that once formed them. Its black hole will still spin at the core, a silent witness to ages past. Globular clusters will still orbit like ancient storytellers, tracing paths written during the galaxy's youth. The cosmic web will stretch around it unchanged in its colossal beauty, indifferent yet eternal. If there are observers in that far future on Earth or on some other distant world, their night sky will be different. The stars they see will not be the same constellations we know. The bright band of the Milky Way will be replaced by the smooth glow of a giant elliptical galaxy, its light more diffuse but still magnificent. The universe beyond will have grown quiet as distant galaxies vanish beyond the cosmic event horizon, leaving behind only local structures, yet they will still be able to look inward. They will see the relics of the galaxy's early days, its oldest stars, its halo, its central black hole. And if they study carefully, they will be able to reconstruct the story of the Milky Way, how it was born from a cloud of dark matter, how it grew through collisions, how it spun and warped and thrived as a spiral galaxy filled with light. Every star in the sky will be part of that story. So will every grain of dust, every orbiting planet, and every forgotten stream of stars drifting through the halo. The galaxy we know today is only one frame in a film that spans cosmic time. We happen to exist in a luminous chapter, a time when spiral arms blaze with young stars and the night sky is full of wonder. This is the Milky Way at its height, but its story is larger than us. It began billions of years before life on Earth, and it will continue long after our world has faded. To understand the Milky Way is to step outside our brief moment and glimpse the vast river of time that carries galaxies through the universe. We are passengers on a small world orbiting an ordinary star drifting through one arm of a spiral galaxy. Yet we belong to something vast, a structure that has shaped everything we see in the night sky. And for a brief moment in cosmic history, we get to look up and witness it.